Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the joint probability density function of multiple continuous random variables. In the previous video, we explained that if we define multiple continuous random variables within the probability space, things work out. We can characterize those random variables in terms of the probability that they belong to certain intervals at the same time, or equivalently to the probability that they belong to rectangles or hyperrectangles. All of that is well defined mathematically. However, we never define random variables in terms of the underlying probability space, as I've been saying as a broken record since we started talking about random variables. Instead, we need some kind of tool to actually encode all the probabilities that we're interested in, and that is what we're going to estimate from data. In the case of one discrete random variable, that's the probability mass function. In the case of one continuous random variable, that's the CDF or the PDF. In the case of multiple continuous random variables, we already talked about the joint cumulative distribution function, the joint CDF, in this previous video where we defined multiple continuous random variables mathematically, and we saw that it was very difficult to deal with. Because of that, for when we have multiple continuous random variables, in the majority of cases, we use the joint probability density to manipulate them, and that's what we estimate from data. So today we're going to define that object and learn about its properties. Let's get to it. We're going to talk about the joint probability density function. We should remind ourselves, the goal is to define probability density for multiple continuous random variables. And where I was going is that we should remind ourselves what probability density actually means. So remember that the probability density, here I'm drawing the probability density of some random variable at a certain point, tells us the density of probability at that point in the following sense. If we have an interval of width epsilon, where epsilon is very, very small, the probability that the random variable is within that interval, because remember that the probability that the random variable is equal to a single point is 0 because it's a continuous random variable. The probability that within this interval of width epsilon is equal to epsilon times the density. So you can think of the density as probability per length. Okay, pointwise when we make the length go to 0. All right, so now how do we define the probability density of two random variables, or equivalently a 2D random vector, at a certain point AB? Okay, so the first random variable is close to this point, the second random variable is close to this other point. Well, it's natural to consider the probability that one of the random variables is in an interval close to, in this case, A, and the other random variable is in an interval close to B, so that essentially what we're saying, maybe I should draw this. So we're saying like the point AB is here. So we're saying what's the probability that A is within this interval of length epsilon and B is within this interval of length epsilon. Equivalently, the 2D random vector is within this square of surface epsilon squared. And the density is going to tell us, the probability of being in that square divided by the surface, or the area, I shouldn't say surface, the area of that square. So now this probability is going to be this density is going to be probability divided by area. This is the same as if you were considering maybe the mass of a thin sheet of some material, and you have the density of the material with respect to the area. Or if we were in 3D, that's perhaps easier to see, it would be probability divided by volume, and the equivalent would be you have some object and you're looking at its density of mass, which is basically mass divided by volume. So intuitively, that's what the probability density the joint probability density is in multiple dimensions. Now, instead of being the probability that you're in an interval when the length of the interval goes to 0, is a probability that you're in a small hyperrectangle, in the case of 2D, a small rectangle or a small square, when the area goes to 0. Higher dimensions, the probability that you're in a hyperrectangle as the volume, the d-dimensional volume of the hyperrectangle goes to 0. So how do we define the probability density? Again, so here this just by the definition that we've set, it's the probability that you are in this square of area epsilon divided by the area of the square. So now we're going to try to represent this probability density in terms of the joint CDF, because we know that the joint CDF is well defined. It's a pain to deal with, but we know it's well defined because it just encodes the probability that the random variables are smaller than certain values at the same time. So in order to represent this probability as in terms of the joint CDF, we have to do this trick. I'll just repeat it very quickly, where we say we're interested in the probability of being within this square here. So what are we going to do? We're going to take the probability that we are here, that's this guy, subtract the probability that we're here or here, this guy and that guy, and we have to add back the probability that we're here, which is this guy, because this area is subtracted twice. Hopefully that makes sense. And then we divide by epsilon squared. So now we're going to rearrange this in the following way. You will see in a moment why we're rearranging this in the following way. We take up 1 over epsilon, and we consider the difference between the CDF at AB and the CDF at A minus epsilon B divided by epsilon. When this part goes to 0, essentially what we have is the partial derivative of the CDF with respect to this first argument. Okay, this is just by the definition of derivative. Same thing here. Here we have the partial derivative, again, with respect to the first argument at B minus epsilon. Okay, so here the partial derivative is evaluated at B, and here the partial derivative is evaluated at B minus epsilon. Okay, so now we're going to plug that in. We have those two partial derivatives. But now if you take the partial derivatives and you subtract them, but you set this to be B minus epsilon and you divide by epsilon, this is just the definition of the partial derivative with respect to B. So what we're doing essentially is we're taking the CDF at AB and we're taking derivatives in both directions. This is very natural because remember that the probability density in one dimension is obtained by taking the derivative of the CDF, because it's the rate of change in the CDF. So here this is showing us that the way we have defined probability density in multiple dimensions, you need to take into account the rate of change in all of the dimensions, which is why we take partial derivatives with respect to all of the dimensions. And this is how we define joint PDF. We define the joint PDF as the derivative of the joint CDF with respect to all of the entries of the random vector that we're interested in, or alternatively, all the random variables that we are considering. Okay, again, same thing for D dimensions. This is why I said when we were talking about the joint CDF that the joint CDF is still useful from a mathematical point of view, even if we don't estimate it from data. All right, so how do we use the joint PDF to compute probabilities? Remember that a Borel set sounds, depending on how mathematically minded you are, either cool or quite scary, but a Borel set, the only thing that it is a union of intervals. In 2D, it's a union of rectangles. So how do we compute the probability that this random vector is within that union of rectangles? We can basically look at each individual rectangle. If they are disjoint, the probability that you're in that union is going to be the sum of the probabilities. And this can be obtained by just integrating the density over all of those, over all of that set. So I'm not going into too much detail here because the argument is essentially the same as the one we went over when we explained why you can obtain probabilities in 1D by integrating the probability density function. So I would recommend that you go back to that video if you don't remember. But essentially, the idea is that there are kind of two ways of seeing this. You can either represent this in terms of the CDF at different points and just see that you get these probabilities, or you can imagine that you're basically taking little squares, in the case of 2D, little squares of area epsilon square, and you're basically aggregating all of those probabilities in the limit where epsilon goes to 0. That's a Riemann integral that is just going to converge to this. All right, but the bottom line is that the way we estimate probabilities using the density is just by integrating the density over whatever set we're interested in. We'll see an example in a moment. Same thing in d dimensions. We integrate to know to compute the probability that X belongs to some union of hyperrectangles, to some Borel set. We integrate over that Borel set. Let's take a look at some basic properties. What happens if we integrate over the whole space? In the case of 2 dimensions, over the whole of all of R2. So we integrate one of the random variables over its whole possible set of values and the other random variable over its whole possible set of values. Well, basically, this must be the probability that the random variable ends up somewhere, and that probability has to be equal to 1 because the random variable has to end up somewhere. Sometimes for this kind of arguments, it's useful to remember that the random variable is actually a function from a sample space. Sometimes that provides the cleanest proofs. What happens if we do this in d dimensions? Exactly the same. If we integrate everything over all the possible ranges of values, then this has to integrate to 1. Is the joint PDF always non-negative? So here you need to remember something that we derived in the previous video on multivariate continuous random variables, and that's that the joint CDF is non-decreasing in each of its arguments. And because of that, when we take these partial derivatives, we're never going to get a negative value. So the answer is yes, because the joint CDF is non-decreasing in every argument. And this also holds for d dimensions. So this is just to say that a joint PDF is a function that goes from d dimensions to a single number that integrates to 1 when you integrate it over the whole, like over RD, if you're considering d dimensions, and is non-negative. Any such function is also, it can be considered a valid joint PDF. If you're very mathematically oriented, the reason for this is that you can reverse engineer a probability space, as we discussed in the case of a single continuous random variable and also discrete random variables. You can reverse engineer this probability space using the joint probability density to assign the probabilities to define this probability measure. Again, not super interesting, but I guess if a mathematician, corners you and says, why are you estimating this object from data? How do you know that things are fine? Then you can say, well, if it's non-negative and it integrates to 1, I can build a probability space. I'm never going to do it, but I could. Okay, so let's go to a simple example. We're going to use this example of a triangle lake where there's this biologist that wants to know where an otter is, this aquatic animal. And the biologist doesn't know exactly where the otter is, so she models the location of the otter as having constant density. Okay, because she doesn't really know where it is. There's the same chance, if you want, of being everywhere. So that's the way she models it. So now what is the value of the joint PDF? Again, the otter can be here. Oops. I don't know what happened to my iPad. Here. It can be in here, but it cannot be out. It cannot be here. And the density is constant here. So how are you going to compute the value of the density? Maybe think about it for a second. Well, this has to integrate to 1. The area of that triangle is 1/2 multiplied by the density, which is constant. That should equal 1. The density needs to equal 2. Okay, so that's the density on the triangle, and out of it, it's 0. The otter cannot be there. This, by the way, reminds us that the joint probability density actually tells you the local describes the local behavior of random vectors, just like as in the case of random variables, very effectively. If you looked at the joint CDF, then it would be much more complicated to understand the local behavior, because the joint CDF gives you a global description of what's going on with this random vector, what's the probability that it's in sets of that of that shape. All right, so now imagine that you want to know the probability that A is greater than 0.6 and B is smaller or equal to 0.2. Okay, roughly. So you're interested in the probability that the author is here. How do you compute this probability? You integrate the joint PDF over that probability. What's a joint PDF equal to? It's equal to 2. So essentially what we're going to do is we're going to integrate, so I'll draw my picture again, from b from 0 to 0.2, okay? And now when we integrate a, we have to be a bit careful, right? We're integrating a in this direction. We are not integrating it from 0.6 to 1. We're integrating it only up to this line. What is this line? This line equals 1 minus b. So that's why we have a 1 minus b here. So first we integrate with respect to a. We get 1 minus b minus 0.6, so that's 0.4 minus b. We multiply by 2, of course, and now we have to integrate from 0 to 0.2. So, you know, like you do, basically, this is just going to be times 0.2, and then here this is going to be b squared over 2. You plug in the values and you get 0.12. I do recommend that you solve this on your own, and who knows, maybe I'm wrong and you can embarrass me in the comments. All right, so now how would we go about, and this I owe you because I kind of showed you the joint CDF very quickly in the video on multivariate continuous random variables, but I didn't tell you how I computed it. So now we would see how we would go about computing the joint CDF of these two random variables. So imagine that we're at a point here where this is A and this is B. What is the value of the joint CDF? It's the probability that we're here. This is very easy because the density is constant. What is the area of that square? It's just AB. So the probability is 2 times AB. Okay, I don't even need to really do many integrals, but I mean, the integrals are there in case you want to check, but it's 2AB. If I wanted the CDF here, then it gets a little bit more complicated, right? I have to compute this area and multiply it by 2. If I want the joint CDF here, then basically it's this area here, and so on and so forth. If you compute all of these areas and you multiply them by 2, you get this joint CDF. Again, the joint CDF, compare the representation that we obtain from the joint CDF. Someone shows you this and says, look, the author, this is the joint CDF of the position of the author. Very difficult to figure out what's going on. If they tell you, the author has a constant density of being here, yeah, like, I mean, it's a much, much better description because you know what is going on locally, all right? So this is just to further emphasize how useful the joint PDF is with respect to the joint CDF, and that's why we usually just estimate the joint PDF from data, not the joint CDF. So as I said before, once we have a non-negative function that integrates to 1, we have a valid joint PDF. But how do we get that from data? Today we're going to take a look at a non-parametric approach where we don't make any parametric assumptions to estimate the density. In a couple of videos we will see how to do this parametrically. So an issue here is that we cannot use empirical probabilities because the probability of each data point is 0. This is we already encountered in 1D where we were considering just a single continuous random variable. If you remember, the way we went about this is by either computing histograms or, very similarly, the kernel density estimate. What's kernel density estimation? Well, the idea is that you look at your data points and you basically put a little bump on top of the data points, that is this kernel shifted there, and you build your density with these shifted kernels that are located at the available data. As long as that kernel is non-negative and integrates to 1, because of this normalization, the kernel is going, the whole PDF, here we're talking about just the PDF of a single random variable, we're going to see the generalization in a moment. The whole PDF is going to be a valid PDF. Notice, I want you to notice this parameter h. This parameter h governs how fat or thin the kernel is. This is probably easiest to just show through a picture. How do we build the estimate of a PDF using kernel density estimation. Here are 3 data points, x1, x2, x3. The contributions of each data point is basically this kernel centered at the data point. That's for x1, this one x2, and this one is x3. They're normalized in a way where when we add them all together, the area is going to be equal to 1, and this is what we get. This is the estimate. And you can quickly see that how fat or thin the kernels are going to really determine how the final PDF looks like. If the bandwidth is very small, so the kernels are very thin, then we're going to potentially overfit what's going on with almost individual data points. If they're very fat, then we're going to get something that is just over smooth. We're not going to see what structure is in the data. So how do we generalize this to multiple dimensions? Think about this for a moment, maybe pause the video. Well, we can apply essentially the same idea, except that now we need to use kernels that are not one-dimensional. In this case, we would need 2-dimensional kernels that have a certain density, right? So something like this, we can put at one data point, this at another data point, and this at another data point. And if we make sure that the integral of these guys is equal to 1, so the volume under these surfaces is equal to 1, then we're going to have a situation where the whole estimate, when we add them all together, is going to be a valid joint PDF because it's non-negative and its integral is going to be equal to 1. Okay, so here these are the 3 data points. That's the estimate that we obtain using multidimensional kernel density estimation. These are the contour lines, the lines at which the density is constant. Often it's easier to look at those contour lines than to try to plot the actual 3D density. Okay, so the definition of kernel density estimate in multiple dimensions is extremely similar to one dimension. We're basically doing a sum of these multidimensional kernels that are centered at each data point, and they're normalized in a way that the whole density is going to integrate to 1. How fat or thin they are is governed by this bandwidth parameter. And sometimes, if you want, you can also generalize this. Here, the bandwidth is a constant, but you can also generalize this definition by making the one with a matrix so that there's different spread in different directions. Okay, so there's many generalizations of these kind of ideas. And the point is that as long as the kernel is non-negative and integrates to 1, the whole joint PDF is going to be a valid joint PDF. The estimate at the end of the day is composed of copies of the kernel centered at each data point. So here we have a data set where I'm showing you the temperature in Versailles and Manhattan. I found this kind of amusing because this is Versailles in Kentucky, not in Paris, and Manhattan in Kansas, not New York. And this is an estimate that we obtain with a bandwidth of 0.1. You see that some of the structure that we're finding, these are the contour lines, are probably noise. Like this really looks like an isolated data point, not really some important structure in the data. When we use a larger bandwidth, that disappears. If we use a bandwidth that is too large, we might be over smoothing parts that could be informative. Okay, so from here to here, probably we're over smoothing a bit. Here you would have to decide what you actually care about in terms of a metric and use cross-validation to decide what the best bandwidth is, or just take a look at different bandwidths to get an idea of how the cloud of points is structured. All right, so before I tell you what we have learned, I do want to emphasize that this kind of joint probability density estimation is possible when the number of dimensions is very small. In 2D it works, in 3D it works. If you have 20 dimensions, it's not going to work anymore because each of the points essentially is going to be very separated. This is due to the curse of dimensionality. We already talked about the curse of dimensionality in the discrete case, so go check out that video if you want. In the continuous case, it's only worse, right? Because the idea is that you have several dimensions, the possible values of the variables just explodes exponentially. We cannot hope to estimate this joint PDF in a non-parametric way. That motivates using parametric models such as Gaussian random vectors, which we will talk about in another video. All right, so what have we learned? We have learned the definition and properties of the joint probability density function of multiple continuous random variables, and we have also learned how to estimate it from data. And that's all I got. Thank you very much.